Hello. This part here will be dealing with problem solving for Otto cycle. Now, first thing is let us take a look at the questions. Okay, 1 kilogram of air is taken through a constant volume cycle. Now, at the commencement, that means at the start of the adiabatic compression, okay, the pressure, temperature, they are 103 kPa, kilopascal, and 100 degrees C. Now, the adiabatic compression have a volume ratio of 6:1. Now, the maximum pressure cycle is given as 3.45 megapascal. Now, determine for the cycle, part A, the pressure, volume, and temperature at each of the cycle process. Okay. Part B, the heat transfer to the air. Then part C, you have the heat rejected by the air. Part D, you have the ideal thermal efficiency. Part E, you have to find the net work done or the network output and the mean effective pressure. First thing, remember we have to draw your PV and TS diagram. So this is your PV diagram, pressure volume diagram, and the temperature entropy diagram. Now, you have both the constant volume process and on the TS diagram, that's your constant volume line. Okay, both. Then you have isentropic 1 isentropic process and 2 isentropic process 1 and 2. Then you have one isentropic line on the TS diagram. It's supposed to be vertical line, and then the second one. Then you need to put in all the points for the PV and the TS. So then you can put in your point 1, 2, 3, and 4. So that's your point 1, point 2, point 3, and point 4 on your PV diagram. Then on the TS diagram, point 1, point 2, point 3, point 4. So how are we going to see whether this point here is supposed to be point 1? So you have to look back to your PV diagram which we have drawn. So point 1 is at the lowest pressure. So you assume that, okay, due to the lowest pressure, then we will be dealing with lowest temperature. Then the next thing you have to look at is the isentropic. After point 1, okay, so from point 1 to point 2, that is where you have your isentropic. So if this is your point 1, make sure that this is your isentropic line. So that is your PV and TS diagram. So you can put in the arrows. Okay, the arrows are all in clockwise direction. Remember, for PV diagram, the area here is work. And for the TS diagram, the area will be representing the heat flow. Okay, so that is W and that is the Q. So, based on my experience, it is easier for us to solve the problem by putting in all the given data here. All the given data, pressure, temperature, okay, and this pressure here into a tabular form, okay, into a table. So here, what we'll be doing is we have a table prepared. First column here, we put pressure. Then this you put volume, and this you put the absolute temperature. So it's advisable to convert all the temperature which is in degrees C into the form of absolute temperature, that is Kelvin. So and then you have your 0.1, 0.2, 0.3, and 0.4. Then you have your pressure, because the question has says at the commencement of the adiabatic compression. So you have to see which supposed to be your adiabatic compression. So you only have two adiabatic process here, or isentropic, which represented by the red curves or the red lines on the TS diagram. So at the commencement, that means that should be your 0.1. So your 0.1, you are having a pressure of 103 kPa. So if let's say, for example, you want to make it to MPa, so it should be 0.103. You can, instead of MPa, you can put bar as well. Then meter cube per kg or meter cube. Why do I say so? Because the questions has referred to 1 kilogram. So for 1 kilogram of mass, so you can refer to volume as meter cube, or if it is per kg, then you can also put it as in terms of meter cube per kg. Unless it's more than 1 kg or less than 1 kg, so definitely your volume here should be your the absolute volume. Okay, so and then the temperature should be in Kelvin. So you have put in the starting pressure 103 kPa, and then temperature 100. So 100 plus 273, so you have 373. And then based on the question, you have the maximum pressure cycle. They say the maximum pressure cycle. Okay, so which is given as 3.45. So you just put in 3.45. So in this table here, you have the given data, that is the pressure P1, the temperature T1, and the pressure P3. So as you refer to the table, this, one, and this one, and also this and this, they are all unknowns. So when you look into the table, you go by the row. So the first row here, you can see you have got pressure and temperature. So why I say in tabular form, okay, is much better, okay, because it's less complicated. Okay, so from that you can see what are the unknowns, what is the unknown, or what are the unknowns that is in the table. So you can go accordingly to points or process. So if let's say, for example, you are referring to each individual point, state point 1, the only thing you can use is the ideal gas law, PV equals to MRT or PV equals to RT. Okay, state point 2, state point 3, state point 4. As we know from the diagram, point 1 to 2 is isentropic, then point 3 to 4 is also an isentropic process. So you can call this 1 to 2 here as an isentropic process, 3 to 4 as an isentropic process. So when you refer to the first row, as you can see, the part 1 here is unknown. That is the volume. Okay, the volume is unknown. So you can straight away, based on the state point 1 here, based on only state point 1, you can use PV equals to RT or PV equals to MRT. If you use PV equals to MRT, then your mass is 1 kg and the volume is in meter cube. Okay, so from this, okay, we know that 1 to 2 is isentropic, 3 to 4 is isentropic, and then constant volume should be 2 to 3 and 4 to 1. Okay, so you have to analyze the diagrams carefully. Okay, the PV diagram and the TS diagram carefully. Okay, so the first thing you need to do is calculate the volume here. So that is why I have put it as part 1 and then part 2. You can go accordingly or it's up to your choice. Okay, for our example here, always when you are solving the problems or if you are asked to find out pressure, volume and temperature of each state point, then it is better for you to get a table prepared like this and then look into the table, analyze and see what are the unknowns and what are the things, what are the data you should obtain first. Okay, so based on this, we know that we have to obtain or we have to find the volume V1 first, is because in the questions they have also given us the adiabatic compression ratio is 6:1. Okay, so based on the ideal gas law, PV equals to RT or PV equals to MRT. In this case, you can use both because it's 1 kg. Okay, if it is less than 1 kg or more than 1 kg, definitely you have to use PV equals to MRT. Okay, so we know that for A, since the question say it is A, so we must know that for A, the specific gas constant, that is the uppercase letter R, should be equals to 0.287 or 0.2871. Okay, so and then the temperature T1 is 373 and the pressure given is 103. So you can straight away put 103, which is in kilo, and then your R here, which is 0.287, is also in kilo. So you are safe by not multiplying the 10 power of 3 on both of these 0.287 and 103. So what you get is your specific volume of 1.039 meter cube per kg, or it can be in meter cube as well, because the mass is 1 kg. So once you have found this, okay, once you have found the volume at state point 1, so at state point 1 now you have the pressure, you have the volume found, and the temperature given. Okay, so now the next thing is, now there are no other single state point you can do to find out any of the properties here. The P, the V, and the T for state point 2, all of them are unknowns. And then at state point 3, you have volume unknown and temperature. You have the volume unknown and the temperature unknown as well. Then at state point 4, you have all of them are unknowns. Okay, so you have to be very careful for your next step. So what we need to do is, since I have marked here as part 2, you should find or you should consider, then please refer to the compression ratio or the volume ratio, which is given here 6:1. Okay, 6:1. So the part 2 will be based on the volume ratio, So since the volume ratio is given, so usually the volume ratio we have is usually Vmax over Vmin. Okay, Vmax over Vmin equals to 6. So if let's say, for example, you want to find V2, then you should have V1 divided by 6. So the V1 we have found here, 1.039, and then divided by 6 based on the ratio given here. Okay, then you have your volume V2 found. So once you have your volume V2 found here, then at state point 2, you have one value or one data that you know, that is the volume. So we cannot use the ideal gas law here at state point 2 because there are two unknowns. Okay, only the volume you have known. Okay, so what you need to do is, now since 1 to 2 is an isentropic process, from the diagram you should know, okay, before you draw also you should know that 1 to 2 is isentropic. So based on isentropic, okay, we can use this formula here. This is the temperature volume relationship where it is to the power of gamma minus 1. So now these formulas, as I have told you earlier, it can only be used, okay, if you are referring to an isentropic process. Okay, so for isentropic process, you can use any of these relationship here. This is temperature pressure, which is to the power of gamma minus 1 over gamma. This should be gamma. And then temperature volume relationship to the power of gamma minus 1. Pressure to volume relationship, okay, is to the power of gamma. Temperature to volume is to the power of gamma minus 1. Temperature to pressure, it should be power of gamma minus 1 over gamma. So since we are having the questions has given us the volume ratio, so that is better for us to use the temperature volume relationship. The temperature volume relationship. So since the T2 is unknown, so therefore we take T2 to be the subject. So once, okay, you have T2 as the subject, V1 over V2, which is the volume ratio, multiplied by V1 over V2, which is the volume ratio. Take it to the power of gamma minus 1 first, then multiply by T1. You should get the temperature of 763.72 Kelvin. So that means the temperature here you have found. Okay, so based on the second row of in the table, you have already got the volume, which I have taken, and the temperature. Okay, so now the next thing is when you look into state point 2 again, now when you look at it, okay, there is only one unknown. If you want to continue with using your isentropic process, okay, or ideal gas law is up to you. Okay, you can use isentropic process, which okay, where you should refer to the pressure volume relationship. Okay, so if let's say for example you are referring to ideal gas law, then you have to take pressure here to be the subject. Okay, so we go to the next slide. So we have found this, and we have found this and this just now. Okay, what we need is the P2. Okay, before we can find out the V3 and the T3 and also the P4, V4 and T4. So based on this, okay, that is your PV and TS. It's just for our reference here. So we can straight away use the ideal gas law to find out the pressure. So the pressure found is 1265.52 kPa. So you have found, that means you have found this as well now. Okay, so I take it in green. So these are the values you have found. So and at state point 3, as you can see, okay, this 3.45 is given. And we know that V2 is equals to V3, right? From here, from your pressure volume diagram, you can see here, this is your constant volume line. And here is where you have your V2 is equals to V3. Okay, V2 is equals to V3. Sorry. Okay, so since V2 equals to V3, that means you know this value as well. So based on this, now you can find out the T3. That is the only unknown that you need now. Okay, the only unknown that you need to find at state point 3. So you can refer to ideal gas law because it is only referring to state point 3 and that is the only value is unknown. So you can use ideal gas law. Okay, we know that V2 equals to V3. You can write it as meter cube or meter cube per kg because the mass given is 1 kg. So find out the T3. Okay, using your ideal gas law. So you found out the temperature at point 3 is 2082.02 Kelvin. Okay, that means you have found this now. Okay, so now the state point 4. Now state point 4, we know that when you refer to your PV diagram, you can see this line here is constant volume. Okay, so V4 is equals to V1 here. V4 is equals to your V1. Okay, then you know what is your V4 now. So now the next thing is, again, this value here is unknown for the time being. This value here is also unknown for the time being. Okay, so what you need to do, okay, remember 3 to 4 here, the process 3 to 4 is isentropic. So you can use the isentropic relationship, and we know that the volume ratio is the same, that is 6 to 1. Okay, or you can put in the volumes now by now. Okay, and then the gamma, remember for A is standard 1.4. So you can find out your T4 as this, 1016.85 Kelvin. So you have this value here. Okay. So then now, the next thing is your pressure P4. So you can apply ideal gas law again. You can apply ideal gas law now here, because you have got this value and you have got this value as well. So now, apply ideal gas law, you can find out your P4. Sorry, this value here. This value here. Okay, so you have found P4. So I erase it off. Okay, so that means the table now is complete. So once the table is complete now, it is easier for you to find whatever to be found. Okay, first thing is your heat supply. Here is your heat supply. Remember, we use this CV T3 minus T2 for A, CV standard 0.718. So you can find out heat supply as this. Then for heat rejected, again CV T4 minus T1 this time. Okay, then you can find 462.28 kilojoules per kg. That's your heat rejected. Then once you know heat supply and heat rejected, we know that net work is actually equals to heat supply minus heat rejected based on the engine cycle. Okay, so divided by your required input, that is your heat supply. So just put in whatever you have found here into the formula, then you can find out your thermal efficiency. Or you can also find out your thermal efficiency by using the formula of 1 minus 1 over RV to the power of gamma minus 1, which we have proven it earlier. Okay, you can use this directly where RV is 6. Okay, given in the questions, the volume ratio is 6 to 1. The gamma is 1.4 for A. Okay, so you can use this formula as well to find out the thermal efficiency. So now I erase it off. Okay, so that is something good about podcasts, because when you refer back, okay, you can see whatever I have shown, and then you can refer to as many times as you can. So now, okay, so once you know, okay, actually you have actually found out the network. Okay, you don't have to use this network equals to heat supply times the multiplied by the thermal efficiency again. So this is an alternative way. Okay, once, if let's say in the question they have given you the thermal efficiency, once you find out your heat supply, okay, if heat rejected is unknown, you can straight away find out your network. This is an alternative way. Okay, other than this, you can also use heat supply minus heat rejected as what is shown here. Okay, then the next thing that you need to know is the mean effective pressure, MEP. So the mean effective pressure is defined as net work out divided by the length of PV diagram. So when you refer back to your PV diagram, the length of the PV diagram should be the V1 minus V2, okay, or V4 minus V3, the outermost point in the PV diagram. So you've got both the volume, and then you have already found the network. It can be kilojoules per kg or kilojoules in this case. Remember, because the mass is 1 kg. So you can find out your mean effective pressure.